I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism podcast, an exploration of the past, present, and future of material science and engineering. I'm Andrew Falkowski. I'm an undergraduate student in material science and engineering here at the University of Utah, and I'm joined, as always, by my co-host, Taylor Sparks. Taylor, how have you been? What's new? And what have you been listening to?
Great questions. I have been listening to, it's grant writing season for me, so when I got to get in the zone, I can't have lyrics. I've been listening to just like chill hop, just something that won't distract me, and there's a couple go-tos that I like there. And what's new, I actually gave a TEDx talk for TEDx Salt Lake City, which was so cool.
Okay, what was it on?
So we're going to do a whole episode on it in the future, probably the next couple months. But it was on materials informatics, which is, like the name kind of suggests, it's material science, but it's merging that with the field of data science, basically trying to address age-old problems of material science, but with data science techniques.
That's super cool. You'll definitely have to let us know when that's available so we can listen to it.
Absolutely. What have you been up to?
It's that time of the semester where you just have so much caffeine in your body and so little sleep that it hardly feels like I'm actually alive at this point. But we're only a week away from fall break, so if I can just hold on for a little longer.
Super cool. What do you got plans for? Are you going to go do anything fun?
I think I'm just going to go home and sleep.
Just decompress. Detox from the caffeine for a minute?
Yeah, definitely need a break.
Sounds good. Back to Idaho.
Back to Idaho, yes.
Very cool. So this month, we have a really exciting topic. It's titled Seeing with Electrons. And in 2019, maybe you've seen these images before and wondered where you got them. But have you ever noticed that in science, sometimes you'll see an image of like a fly's eye and it's all the little facets, or like a spider up close and you see all the hairs on it. It looks like something out of like a Godzilla movie, just terrifying. So the tool to capture those, you could use an optical microscope, but it has some limitations. Instead, oftentimes, these are captured with a scanning electron microscope, and that's the subject for today's episode.
Okay, so you're talking about an optical microscope, and you tell me that it has some limitations. But is there a point where something gets so small that we can't use just light to look at it?
Yeah,
and
absolutely.
Why is that?
And even with the naked eye can look down to, I think it's like tens of microns, basically. So to put that in perspective, like a human hair is like 10 or 20 microns wide or something like that. And that's pretty close to like the resolution that our eye can see unaided. If you want to go smaller, this goes way back to like the 17th century. Microscopes have been one of these core staple tools that the science community has used. In the 17th century, actually there was this Jesuit monk. Check this out. I read this in studying for this. He's a Jesuit monk. This was right around the time when they were discovering germs. He used a microscope. This guy's name is Athanasius Kircher, and he wrote this book. The chapter, it's all in Latin, but this chapter has this little section, which if we translate it, it says, concerning the wonderful structure of things in nature, investigated by microscope. And he states, who would believe that vinegar and milk abound with innumerable multitude of worms? Just horrifying, right? So scientists for a long time have been looking at the natural world around us using microscopes for hundreds of years at least. And I think that in general, humanity has always been fascinated by this whole tiny world that exists smaller than our eyes can see. And so tools that allow us to envision that really captivates imagination in book writers, in Hollywood, right? Movies like Honey, I Shrunk the Kids, which here's a clip from that.
We're now a quarter of an inch tall and 64 feet from the house. It's the equivalent of 3.2 miles. It's a long way, even for a man of science.
Yeah, I mean, we've always been fascinated with the tiny world around us and imagining what it would be like. But an optical microscope, it can only get us so far because it uses visible light. Our eyeballs, we've evolved to see certain ranges of light. And basically because we're seeing with visible light, and that visible light has a wavelength, which is kind of big compared to the things that we'd like to look at, it leads to some problems. So we can see in the visible spectrum, which is somewhere around like 300 nanometers to 700 nanometers, at least thereabouts, But that's pretty big, 300 nanometers. Atoms are far smaller than that, right? They're angstroms apart. So how are you ever going to be able to visualize something with something whose wavelength is way, way bigger than that? This is just a fundamental problem in optics. And so visible light has this problem of resolution. And in practice, the smallest that we can get, well, there's an equation that says that the smallest resolution you can get is the wavelength divided by 2 times the numerical aperture. And the numerical aperture, that's going to be the refractive index in which the lens is working, right? And multiplied by sine theta, where theta is the largest half angle of the cone of light that enters or exits the lens. Or in other words, basically, if you're going to use a lens in light, like you might have done when you were looking at the electronics that you were working on, then your lens is in air, which means that your numerical aperture, sort of at best case scenario, is something like 1. And so you could pick a different medium. Instead of looking at an air, you could immerse it in oil, and that gives you a little bit of improvement. It goes from refractive index from 1, or numerical aperture from 0.95 all the way up to 1.5. But in practice, like the best you're going to be able to do is somewhere around a couple hundred nanometers. You're never going to be able to see atoms with an optical microscope. That's not to say that they're not doing cool things. As recent as 2014, the Nobel Prize in Chemistry was actually awarded to some people who worked on an innovation in optical microscopy called super resolved fluorescence microscopy, which basically gives you an additional ability to look at things even smaller.
Okay, so then if we want to look at something smaller, we can't change our aperture. We're kind of fixed in terms of the materials that we can use to look through things. But so does that mean we have to change the wavelength that we're looking at? We need those to get smaller if we want to look at something.
Yeah, bingo. Longer wavelength would be something like infrared, and shorter wavelength, that's going to be like ultraviolet. And you could move smaller and smaller. Or even better, what if we could take electrons, right? You could take electrons, we can accelerate them to really high energy, so they're moving really fast. And then we can use the de Broglie wavelength, which you learned about in physics and probably never used since. But turns out if you use the de Broglie wavelength, electrons can have a really small wavelength. For example, if you take an electron and give it 20 kilo electron volts of energy, its de Broglie wavelength is 8.6 e to the negative 12th meters. Or in other words, it's picometers, 1,000th of a billionth of a meter. These are tiny, about 100 times smaller than atomic separation. So this should, at least in principle, be able to visualize atoms.
So another limitation that if you've ever used an optical microscope, you spend like 10 minutes trying to like adjust the focus to try and get that image to something clear where you can actually see what you were trying to look at in the first place. And a lot of that stems from the very limited depth of field of visible light.
Yeah, like literally like the vertical region, which can be in focus at the same time, is really small. For example, if you're looking at 100x magnification with a numerical aperture of 0.95, so basically in air, your depth of field in microns is 0.2. So 200 nanometers is what's in focus in terms of height. So that's not very tall. Or in other words, it's hard to look at a big three-dimensional object because you only see this little plane of what's in focus at a time.
Mm-hmm. Everything else. If you've ever seen those pictures where there's like an object that's centered like a flower, for instance, that's very clear and distinct, and then the rest of it's kind of blurred, that's that depth of field that we're talking about.
Yep. So what's really rad is that if you use electrons, not only can you get tiny wavelength, which should theoretically put us in the resolution range where we want to be to see atoms, but because we can use these things, we can accelerate them very fast and we can confine them to a tiny little beam, and that means we can pass it through a tiny little aperture. And basically, if you want to calculate depth of field, it's equal to a number times the working distance divided by that aperture. So what's great is these electron microscopes, you can have a really big working distance, which is the distance from the column of your sample where it passes through the aperture all the way to your sample. And you can do a tiny little pinhole. And so you can essentially have almost infinite working, you can have almost infinite depth of field. So you can look at all sorts of things that are high and low, and it's all perfectly crisp in focus, which is fantastic for scientists. So Andrew, we've got these amazing tools. They've got better resolution. They've got amazing depth of field. How did we get to this point?
Well, there were a series of discoveries about electrons and how we can manipulate them that led us to be able to actually develop a tool that would allow us to both focus them and actually read signals from them as well. So the first, as you already sort of talked about, was in 1923 from Louise de Broglie, who introduced the idea of frequency and wavelength for particles like electrons. So that's what allows us to actually discover that very short wavelength that allows us to see much smaller details. Okay, so then the next thing that was really important is, right, okay, we have electrons, they have a wave, we can accelerate them, but you're just bombarding a sample all over, even on the sample holder with electrons. It's not really useful in this sense. So in 1926, Hans Busch shows that there's a focusing effect when you put a magnetic field, sort of a symmetric magnetic field, and put a beam of electrons through it. It can focus it down into a narrow beam. And so we can actually direct where the electrons are going and remove the scattered nature of it.
Yeah. How would you do that with light? Like, I don't know how you do that with light. Instead, they basically bounce light off of things and you can try and focus it that way. But here, you can actually bend the path of the electrons, right? Which is pretty cool. And that's why you can shrink them down to this tiny little beam, which means you can pass it through a tiny little aperture and get wonderful depth of field, stuff that you just can't do with the light.
Mm-hmm. They're almost perfect for this application because of their charged nature. We can manipulate them in a way that we couldn't do otherwise for light.
Okay, so the year's 1928. It's in Germany. You've got Max Knoll and Ernst Ruska, who are really fascinated with this idea of electron lenses and potentially shrinking them down because then you could visualize things with them. They're working on it, and yet the first patent that shows up is not from these people. It shows up from Siemens Schukertwerke. That's where the first patent is. This guy named Reinhold Rudenberg, an employee of Siemens, he's the recognized patent holder there. What's interesting is that he submitted the patent, but there's no record that he actually made anything, which is this interesting thing about patents that you don't have to demonstrate that you make it. It's the idea, right?
Right. There's a series of letters between him and some of the people who actually were working at it, Ernst Ruska and I think it's Max Steenbeck. And this Rudenberg visits their laboratory and hears about what they're doing, and then he comes back and patents it. So I can't imagine that they were on good terms after that.
I'm guessing not. Okay, so that was 1931. There's still no SEM or TEM, microscopes, electron microscopes out there that you can buy. 1933 rolls up. Ernst Ruska constructs the first two-stage scanning electron microscope. It's got 3 of these magnetic lenses, which again sort of take this beam of electrons and squish it down to a small thing. It's got a condenser, it's got objectives, it's got the projector. And he's able to image cotton fibers and aluminum foils. He gets a magnification of 12,000x, which is a higher resolution than if you were to try and visualize this with a traditional optical microscope. So in the years that follow, you start seeing publications on electron optics, right? They had all been in German previously. Now they're showing up in English. And in America, people are starting to try and make these things, right? In Washington State College in Pullman, an SEM is constructed in 1935.
You also start to see some very primitive SEMs being constructed in Japan, which kind of makes sense because during this sort of timeline, Japan and Germany were allies to some extent. And
oh, that's interesting.
Mm-hmm.
That is super cool. So tell us about Otto Scherzer.
Okay, so Otto Scherzer starts doing a number of experiments with these, and he's interested in seeing the properties and what sort of effects are we going to see. And he comes across 2 sort of effects that he noticed. The first is spherical aberration, and the second is chromatic aberration.
So first off, an aberration, that's something that makes it so you can't get the resolution that you want out of your microscope. It's limiting your ability to use the microscope.
Right, essentially. And he finds that spherical and chromatic aberration are things that a factor into optical microscopes as well. We apply them in terms of a coefficient when we're making calculations with them. But he's the one who discovers that there's an aberration coefficient for electron lenses as well. And these are actually, what's important about this is that he finds that they are non-vanishing and that they're always going to be present. And even if you design your SEM to even like the tightest tolerances and with enough skillful design, you could never remove them. Okay, but what do actually these things mean? So the first is spherical aberration. So if you think about a beam of electrons being passed through a magnetic field, this beam's going to be non-uniform. The electrons are going to be quite scattered. You're going to see a distribution in terms of the distance from the center of this beam. And so in spherical aberration, essentially what happens is the outer electron waves are going to be focused and affected by the magnetic plane at a different rate than the electron waves that are towards the center of this beam. And so what ends up happening is you get a sort of a difference in terms of the focal point. And so if you can imagine 2 different planes that are forming in terms of the focal points, those inner electrons that are affected by the magnetic beam are going to focus at a different plane than those outer ones.
I see.
And so that difference in focal points will blur your image.
Gotcha. So what about chromatic aberration?
Okay, so this stems from the fact that electrons can have different velocities and energies associated with them. The main way that we produce electrons, well, one of the ways that we produce electrons in an SEM is that we heat up a tungsten filament, and we heat up to like 2,000 Kelvin, something in that range, and it offshoots electrons. But the energies and velocities of those electrons
It's got to be all over the place.
Yeah, they're not random, but there's a wide distribution of them. And so because they're going at such a high speed, they're going to be affected, or at different speeds, they're going to be affected by that magnetic field differently as
so
well.
you're never going to get perfectly focused there either.
So if they're moving with a high energy and very quickly, they're not going to be as deflected as much as those that are moving slowly with a lower energy. And so because of that, that's when you get another one of these difference in planes of focus, and it creates a blurred image. And so
Gotcha.
Otto Scherzer, what was important about his discovery is that you can't actually remove this as much as you can, as much as you try, just due to the nature of electrons.
Okay. So 1937, you've got a guy named Manfred von Arden. And what's cool about this guy is he was like one of the pioneers in the early days for like cathode ray tube TVs, where you can make, if you put this fluorescent, stuff on the screen and you bombard it with electrons, it shows up with color, and you can make all of a sudden TVs and all sorts of cool things. And so he had been one of the pioneers who figured out how to raster that, make it scan over and over on a certain pattern so you could actually make images appear over time. And he took this knowledge and he applied these same types of sort of scanning coils, but he put it inside of a transmission electron microscope to create the first time a scanning transmission electron microscope. So in other words, instead of the beam just going down the column from the tip through the optics where it gets condensed and focused to your sample and hitting one point, he was the first person who let it raster. Think of like a typewriter. It's moving along the lines and it rasters over and over, creating these lines, and then all of a sudden you can see everything that gets rastered. It's like a two-dimensional image is the result of that rastering. So 1937, that same year, they set up one of these SEMs in London, and the resolution was basically comparable to a light microscope.
Yeah, so at this time, really you're not seeing – I mean, this is one of the things that you mentioned that initially people weren't really that enthralled with the idea of an SEM. It started with a TEM because they're like, oh, okay, a TEM has so much higher resolution than an SEM. Why would we want to do this? Or if the SEM is just comparable to an optical microscope, what's the point? And so from here we start to see this sort of transition where Ernst Ruska, he contacts Siemens, and they go and they start setting up an ultramicroscopy laboratory in Berlin. And their goal was to try and put enough money into this that they'd be able to create a better SEM than what was available at the time. And they are able to achieve this, although within the literature there's some debate regarding what resolution they were actually able to achieve. Ernst Ruska himself claims that they were able to achieve a resolution of 7 nanometers, but there isn't any other confirming sources on this.
You know what's crazy though? Even though this was like this new tool available, interest kind of died off over the next couple decades. Like in the 30s, it was boomtown for electron microscopy. Electron optics was a big deal. But in the 40s and 50s, at least for the scanning electron microscope, not the transmission electron microscope. And again, transmission, the big difference is that the beam of electron passes through your sample, and that's how you do your visualizing. And on the other hand, scanning electron microscopes, we're looking at bulk objects where it's not going to pass through it. So how that visualizes it, we'll describe in a moment. So despite this interest, what was surprising is that in the decades that followed, research kind of fell off. It focused more on transmission electron microscopes and less on SEMs. And what's cool, there was this group in Cambridge that decides to pick it up again. This is led by Charles Oatley and some of his students and others. And they build one, and they get it up to a resolution of 50 nanometers, which is better than an optical microscope, but not anywhere close to what they're getting at TEMs. But they did notice, and they published for some of the first time, these really striking 3D images, taking advantage of the depth of field of these SEMs, and that was exciting. And so Oatley had this idea, like, what if we could make these microscopes widespread in use? And so he actually hired a market study, and this is what it says about it. Somebody who knew Oatley firsthand said that he once told him the following. When the SEM was being considered as a commercial product, a group of marketing experts were sent out to make an evaluation of the number of SEMs that could eventually be sold. Hang on to your hat. They came back with probably 6 to 10, and then you would saturate the market. Or in other words, the whole world doesn't need this tool, maybe only 6 or 10 of them, and that's all that the world could ever use. What's remarkable is how wrong that was. Today, scanning electron microscopy, SEMs, are among the most common characterization tools. There are tens of thousands all around the world. And our department alone has 2, and it's remarkable how common they are. The university has another 10 probably.
Okay, rounding out the history segment, we have one last major thing. So we talk about these SEMs really coming online in the 1930s, but we don't actually see a commercially available SEM until 1965. And that comes from the Cambridge Instrument Company. And they call this first SEM the stereo scam. Okay, so you might be wondering, you've heard a bit about the history, you know that it involves electrons, there's some sort of magnetics involved in focusing them, but how do they actually work? Well, the first thing that you need to consider is a source of electrons. So we have two options possible. So earlier I talked about using a tungsten filament and how if you heat this up enough, electrons will start to leave the material in a varied distribution of energies. We call this a thermionic cathode, and by heating it up enough, you put so much energy into these atoms that the electrons have enough energy within them to sort of overcome any sort of quantum barriers and actually leave the atoms.
That's right. We take advantage of this with tungsten light bulbs in our homes, right? The reason that we see them is because there's energy coming off of them. Now, there's another way to get these beams of electrons, and that's called a field emission scanning electron microscope, FE-SEM. These are more expensive, but they're better. They have better resolution. They've got a wide variety of things. For example, they can operate at different energy, a broader energy range. How these work is you've got a sharp little tip of metal, but instead of using heat to heat this thing up and cause it to start bombarding electrons, you instead apply an electric field between that tip and something nearby to it, and it's a big electric field. And what it does, even though your electrons in the metal don't have enough energy to be stripped away from it, when you apply that big enough field, they can sort of tunnel through that barrier and come out. And so you can change their energy by changing the field at which you pull them out. So this is a really powerful tool to get additional, not only different energies of wavelengths, but you can collimate them more carefully because they're all closer to the same energy when they exit. So you can fix some of that problems with chromatic aberration that you mentioned earlier.
Okay, that's super cool. Okay, so now we have a bunch of electrons that have been emitted from our electron gun of sorts, whether we're using field tip emission or the thermionic cathode. But, we just have a bunch of electrons now. How do we actually get them to a point where they're going to be useful? So the next thing that we actually want to do is electrons are charged, right? Typically your thermionic cathode has some sort of positive charge. It is a cathode, for instance. And so what you typically want to set up is an anode near that. And the potential difference between the cathode and the anode is enough that the electrons will accelerate towards the anode. And the anode is typically circular with a borehole in the center so the electrons can go through. So that potential difference accelerates the electrons up to a useful speed. So now they're moving very quickly, but they're still scattered. So that's where these electromagnetic lenses come into play, where by using a symmetric circular magnet, an electromagnet that is, we can focus that beam down into a very precise point.
Super, super cool. Not only focus it, but you can change the shape of it. You mentioned earlier this sort of aberration, if it's not perfectly spherical and stuff. Mm-hmm. We have stigmators, which can take, let's say your beam is sort of elliptical in shape. You can pass it through a series of these things that are rotated in different ways to sort of condense that beam and try and make it as spherical as possible, always within some sort of limitation that you can't overcome. Mm-hmm. So you've got these beam of electrons. We've done everything we can to sort of squish them into a nice little sphere, make it as small as possible. We pass it through these different apertures. Once it passes through the last aperture, it's going to continue colliding towards that object, which is going to be your sample.
Okay, so it's hitting the sample, but how do we actually move it around? We talked about the idea of doing a raster scan across our sample. And so that's where another series of electromagnetics come in that's controlled by some sort of raster generator that will direct that beam even further, that focused beam, along our sample and allow us to image different spots.
It's pretty incredible that we can have such precise control over tiny little electric or magnetic fields to move these things, on a whim, to move them exactly wherever we want. It's pretty rad. Mm-hmm. Okay, once it hits your sample, though, that's where all sorts of crazy things start to happen. You've got, first off, when it hits your sample, it's going to go into your sample some way, some distance. The distance is going to depend on your sample, how much it absorbs electrons, but also the energy of your electrons. Obviously, higher energy is going to penetrate deeper. Now, as it goes into your sample, it's going to get absorbed, but not before doing some things. First off, it might crash into some of the electrons inside the atoms in your sample. If it does that, it might eject them. We call these secondary electrons. Okay? These ejected electrons are secondary electrons. Now, there's other electron transitions that can happen. Once you open up a hole, then other electrons that were at a higher energy level, say higher shell, they can collapse down to fill that hole. The analogy I had when I took a class on this as a student ages ago was, imagine you're at a really cool concert and somebody gets up and leaves a few rows up from the stage. Would you just stay far away, or would you go down and fill that spot? You're going to go fill it up. And electrons do the exact same thing. But since energy has to be conserved, and they were at a higher energy level before and they're going to a lower one, they have to give off something with that difference in energy, and that's going to be an X-ray. That becomes important later. Now, another type of energy reaction that can occur is backscatter. What is backscatter, Andrew?
So this occurs that, let's say that the electron actually manages to miss hitting other electrons, but there's still this big nucleus that exerts a number of forces and takes up quite a bit of space within the atom itself. And so, if I understand this correctly, the electron will have some sort of elastic interaction with the nucleus of the atom and almost bounce nearly directly back.
So it doesn't
in the direction
it's not
of
like
the
it
beam.
hits the nucleus and bounces. It gets close to it, and it's kind of like gravity, where
sort of like
when we
when
want to
we-
go to the moon, we whip past maybe another planet and then go to Mars or whatever. It takes advantage of that interaction by passing close to it, and then it slingshots it back kind of the direction it came from.
Okay, that makes sense. Yeah, and so the electrons there are going directly back towards the beam, and the speed at which they're going back towards the beam and the amount that they're doing depends a lot on the number of protons and the size of that nucleus.
So you've got your beam of electrons that are really high energy crashing into your sample. You're generating different types of electrons. Some of them are secondary, which is a different electron gets kicked out. Some of them are the same one that gets slingshot right back up. How do we actually visualize with that? We have to have a detector. So they take a detector and they typically make it slightly positively charged. So as the electron gets ejected, let's say it's a secondary electron, as that thing gets ejected, it's going to feel that positive charged electric field and it's going to be drawn towards the detector, and it's going to count those things. And as you raster it, you're keeping track of how many show up from each spot. If there's a lot, then you get a nice bright spot on your image. If there's not many, it's a nice dark spot on your image, okay?
And that corresponds to a current that's generated from those electrons.
Absolutely.
And the reason, so we talked about earlier, there was those people from Cambridge who made that really interesting discovery about being able to visualize 3D shapes. So how does that actually work with an electron microscope, right? Because a lot of the ways that we perceive depth come into play because we can see shadows or there's a lack of light around something, but electrons don't really cast shadows, so how are we going to see something like that? Well, it stems from the number of electrons that are ejected. If there's a hole, for instance, like a pore, and an electron goes in there, it's going to be much harder for those electrons to escape out of that hole, and so that's why we see it darker.
That is so cool. So it's an optical illusion. It's true. It still looks like it's darker because it's further away, but in fact, what you're seeing is just less signal gets out. So yeah, sure enough, imperfections like edges and protrusions, these show up as brighter, which makes for really compelling, these striking sort of 3D looking images. Okay, we're going to go ahead and take a break. And when we come back, we're going to talk about some of the really unique things about why SEM is still a useful tool, even though it doesn't have the resolution of TEMs.
Okay, Taylor, I'm taking this class, MSc 3010, Materials Processing.
Okay, that's a good one.
The way that it's divided up is to do 3 labs. The first one that I did was a ceramic lab. And I produced these alumina ceramics.
Okay.
And I was just given an alumina powder to use. I had no control over
Whatever we had on the shelf.
Pretty much was this, I put it in a more academic way, but it was essentially just a big old bag of alumina.
Okay.
And the ball milling machine was broken, so I just had to take whatever distribution of particle sizes I had and just throw this into a ceramic.
This sounds like a bad idea for ceramic processing.
Yeah. It ended about as well as you would expect. So I was looking at my ceramic samples post-fracture after some of them crumbled, some of them broke, as a ceramic should. And I noticed these particles that were not alumina. When I was looking at them under the SEM, they looked very different. They had a bit of a different sort of structure to them. And I was wondering, okay, what are these? And I eventually came to the conclusion through some SEM methods that we'll talk about after the break that these were contaminants that were present within my sample. And what I also noticed was the large particle size created lots of pores in my ceramic as well. And so I was like, okay, I need to find a new source of alumina. I can't just use this big old bag of random alumina that I'm finding in the lab. So what do I do? Where can I go? If I go online, I guess like, okay, I can buy it from Sigma Aldrich or Alpha Azar, and I don't really even know where to go. So what can I do?
So there's a great tool for you. It's matmatch.com. Let's check it out. How would you approach this problem? We'd go to matmatch.com. If people haven't used it, check it out, matmatch.com. When you go there, it's a pretty easy to use interface. The very first thing we'll see is a giant white bar where it lets you search for things. So let's punch in aluminum oxide, right? When you get aluminum oxide, it's got a bunch of them with different purities that you can select. And if we just search for that alone, what comes up is 4 different materials from different suppliers, right? So you've got some from Goodfellow or from different companies. Let's pick this one at the bottom, aluminum powder, 99.9% pure from Goodfellow. And when you see this, you can actually see more details about it. It gives you the actual particle size. These things are 45 microns. What's the crystal size? It gives you the exact composition. What's nice about this is that it makes it really easy to find materials, typically from a variety of companies, so you can compare and contrast different sizes or cost in a really easy-to-use way because maybe you didn't know ahead of time who the provider is for some material.
Yeah, and as a student on a quite tight budget, definitely appreciate being able to look at different costs and compare them and see like where my dollar is actually going and how much the change in the amount that I'm spending impacts the quality of the material I'm getting.
One of the things I like that they include on here when they do mention the particle size, they mention how it was measured, that this was done with dynamic light scattering. It was laser diffraction. So that's cool. So this wasn't just like a sieving, rough approximation, that somebody actually measured this. And you can check the spec sheet when they're provided or jump right to the supplier and actually buy some of these materials. So check out matmatch.com next time that you're looking for material, and you'd be surprised how easy it makes finding the material that you need for an engineering application. Okay, so we're nearly out of time, but I did want to wrap up with a couple other things. First off, if transmission electron microscopes can get better resolution, and the only difference here is that the transmission electron microscope has to pass through the sample as opposed to looking at bulk, we wouldn't be using SEMs as much as we do. But SEMs can do some really cool things. First off, and again, we're getting way beyond the 6 to 10, SEMs in the world market fraction that the original study back in the 50s did. The first reason why you'd want to use them is because they have backscatter detection. Now, we talked about backscatter electrons. Those are the ones that get close to the nucleus and it slingshots them right back up. So for these, we're going to use a different type of detector. They typically put it right next to where the beam came from, around the aperture or right next to the aperture, right? And Andrew told us that the ability to backscatter things is proportional to the positive charge of the atom. Or in other words, the higher the atomic number, the more positive charge will be in that nucleus. And so you're going to see samples that are lower on the periodic table with a higher atomic number showing up brighter than ones that are lower. Think about this for a minute. This is amazing. If your eyes could do this, then looking at two pieces of metal that look the same, if one's denser than the other because it's made of heavier elements, it would literally show up brighter. This would be like a superpower. You'd be like Superman if you could look at a parking lot and say, oh, that's a steel car versus an aluminum car because it shows up brighter to your eyes. So this is a really powerful tool because oftentimes when we look at things in material science, they might look really similar, but this all of a sudden provides contrast and you can say, that must be the heavier element, this must be the lighter one. Now, the other incredible thing that you can do with SEM, which is equally powerful, is you can do energy dispersive spectroscopy. Sometimes they call this EDS or EDX. How it works, remember that now what we just described with backscatter, that uses backscatter electrons. Energy dispersive spectroscopy, it uses secondary electrons. So in comes your beam of electrons, it crashes into an electron in your sample and ejects it. And that causes another electron to be like, hey, there's a better seat. I'm going to scooch forward and take that better seat. But it has to give off an X-ray. Every element has a characteristic X-ray that it gives off for each of these transitions. Some of them might be close, but they're typically unique. And so, for example, if you bombard aluminum versus iron, you should see different X-rays given off. And so if you actually, instead of just collecting the electron that comes off, which would be secondary electron microscopy, what happens if you actually collect those X-rays that are given off? if you collect those X-rays and quantify them, you can say not only do you see something and it's bright or whatever, but you can say that that corresponds to a specific element. This is so powerful. Think of this. If you're an engineer and your competitor makes a product and it's better than yours, you can take their product, chop it open, stick it in the SEM, do EDS, and you can say, oh, this is made up of iron and aluminum or whatever else, and you can quantify it. It can be quantitative. Now, how quantitative is always sort of a criticism of this technique. If they're saying it's better than 10%, you should be skeptical, and they need to be using some really carefully calibrated standards. But even if you knew something within 10%, that's enormously valuable. And it works in conjunction with other tools like X-ray diffraction. When you do X-ray diffraction, it tells you potential structures. But if you match that information with the potential elements that might be there, all of a sudden it really reduces the potential space of materials that it could be. So this is a really powerful tool. Now, they can actually even do a little bit better. If instead of collecting X-rays and filtering them by energy, if you combine this with diffraction, so out come these X-rays and you make them actually diffract off a crystal, then you can get what's called wavelength dispersive spectroscopy, or sometimes they call this microprobe. And this will give you very accurate compositions. So this is a really accurate way to determine the compositions of materials in a non-destructive manner.
Mm-hmm. And I imagine it's also really useful for looking for impurities. So if you can see that you're getting some sort of additional powder or some other sort of oxide that seems to be forming, you want to know what's actually occurring or what's that impurity actually made of, you can figure that out and then better be able to determine the root. Or think about jewelry. A lot of times if you buy a piece of jewelry, they'll tell you it's X% gold. You can throw that into the SEM and perform some EDS analysis on it and actually determine what's the actual gold content.
I remember when I was a student, one of the students that I was in classes with, she'd been proposed to, and he gave her a ring. And the very first thing she did, since she worked in the laboratory with one of these microscopes, she put it in there and did EDS on it to make sure that it was diamond carbon and not cubic zirconia or anything like that, which is really cool. But you can imagine looking at interesting core shell particles, tiny little nanoparticles that have a different shell than the inside. You could actually map and figure out what is the shell versus the interior. You could look if there's an impurity phase along grain boundaries or if there's impurities. It's a really cool tool to be able to make images, which you can then overlay with where the elements are. Iron's over here, silicon's over there, and so forth.
And the best part of it is that at least for inorganic samples, is that it's non-destructive. So you can figure out what's in your sample without having to destroy it.
Yeah, super, super valuable technique.
So another really cool thing that you can do with SEMs is we know that we can image a surface. Because of the depth of field, we can see a three-dimensional object, but what we've been able to do even further beyond that is actually use SEM to construct three-dimensional models of things. So there's a couple of ways that they do this. So the first is a photogrammetry approach in which they will tilt the stage and image it at different angles and then sort of triangulate the absolute heights of different features along the surface. The other thing that they'll do is they'll look at essentially the gradients of color and calculate slopes across the surface and then perform integration, find the area underneath, and try to calculate a 3D model from that.
Yeah. I mean, they can do incredible things. They can also slice them away. You can take types of microscopes that are able to ablate away layers of elements. You image it, ablate, image it, ablate. The technology right now is really making some pretty impressive types of electron microscopes.
There was a great demonstration of that where they take a plant cell and then they keep shaving away layers of it and imaging it, and then a computer is able to reconstruct a three-dimensional picture of that cell from those images.
So cool.
Pretty impressive.
Another neat advance is that in the past, when I was a young student, I was working at a company and I was there late one night and I got curious and I took a bug and I put it on the little sample holder. It was like a spider. And I went to look at this thing. And when I went to look at it, I didn't get very good images. First off, because the bug is not made of conductive material, and you're bombarding it with a stream of electrons. And so as it stands to reason, if you bombard it with electrons, it's going to charge. And if it charges, once you accumulate electrons on the surface, they're going to deflect future electrons. And so one of the things that you need to do is you need to coat any sample that's going to be an insulator, an electrical insulator. You have to coat it with something that will conduct electricity. They very commonly actually use gold because you're not putting a thick layer down. It's very, very thin, a few atoms in some cases. And that's enough for it to bombard it with electrons, but then the electrons have a path to be able to leave the sample. So I didn't gold coat it. And then the other mistake I made is that this thing wasn't dead and dehydrated. And when you put it in a vacuum, it basically like bursts and all the guts come out, and it like can actually mess up the chamber. So don't do this. Like this was me being an idiot. So this has been a problem. This was a problem for a while. People that wanted to look at biological samples where you can't just dehydrate them because it no longer looks the same. What they needed was an environmental SEM that allowed you to look at things without pulling this crazy vacuum.
Okay, so these environmental SEMs are, as Taylor described, have a bunch of really interesting properties and can allow us to look at things in a very different way. But, okay, so here's the thing about electrons is that they're so small and they interact with whatever they're passing through. So within an SEM, a vacuum is always pulled so that there aren't any gas molecules that will deflect the electrons or cause any sort of scattering. Okay, but if you want to look at a sample that's wet, you're going to need some sort of gas presence. You can't pull a vacuum on something that's wet. And so how these work is imagine three chambers. Your first chamber, your top, this is going to be the column. That's where all your electron gun and your magnetic lenses are going to be positioned.
That's got to be under vacuum for it to function.
Has to be.
Okay.
At the bottom of this chamber is a hole where the electron beam, the focused electron beam, will pass through. It then enters this intermediate chamber. And so in this chamber, not a total vacuum is pulled. You start to have some gas particles moving in there, but there's another pump that's pumping them as quickly as it can out of there. Finally, it enters this third chamber, this bottom one. That's where a specimen's held, and that is a pressurized chamber where there is gas moving through there, and that's where your sample is held.
Cool.
And
So they basically made like a partially transparent window. The beams can still get through. They can visualize your sample like normal, but you're still able to have the vacuum where you need it to pull the electrons off. Mm-hmm. Cool.
Okay, but you get a number of issues, right? Because there's gas in here, so now that the electron beam's coming in,
they're going to collide with those and interact.
Exactly, and so new considerations have to be made. What ends up happening is they call it an electron skirt, where electrons start to scatter and they'll start to just cover the sample electrons. They're not actually
So do you
useful in
lose
this
resolution because of that? Because it's basically scattering and diffracting off of these molecules?
Mm-hmm, absolutely. But the sample's positioned high enough, the working distance between the chambers, such that
it's reduced. It's a smaller working distance?
Yeah, such that the beam...
It doesn't diffract that much?
It doesn't diffract enough, so that all those scattered electrons just become noise.
Gotcha.
And so what this allows us to do is actually image liquids. So we can put a material or an element in a liquid phase and actually see what it looks like there under an SEM, or, as you were saying, look at live things.
I've seen some of these images. They'll like take water and then they'll make an SEM movie by observing it over time and show how water freezes. And you see actually snowflakes growing and crystallizing out of the liquid. It is super, super cool stuff.
That's got to be awesome. The other thing we have to consider is that because of this gas and the scattering that occurs, there's a new type of – we can't just collect backscattered electrons or secondary electrons the exact same way, because there's a lot of scattering that's happening, and if you put a positive charge on there, you're going to attract all of them, and it's not going to provide accurate signals. So what they do is they use something called a gaseous detection device. And so essentially you have an electrode with a voltage up to several hundred volts, and that's situated on the top of that third chamber. So the electron beam passes through it, hits the material. Then as electrons are ejected, they're going to scatter, and they're going to interact with the gas particles, and that's going to actually knock other electrons out. So you end up having this sort of cascading, almost avalanche effect from the secondary electrons, and it ends up amplifying the signal. And so when it eventually interacts with the electrode, you get sort of an amplified signal, and you can continue to use it as a detection.
That's cool. You'd normally think of like the gases only being a problem, but in here it's actually increasing your signal. That's pretty cool.
The other really nice thing about these is that you don't have to coat your samples anymore, because the gas itself is electrically conductive.
Cool.
And so what ends up happening is charge won't build up because the charge will just dissipate within the gas. And so sometimes if you want to look at very fine details on the surface, if you coat it with gas, you might lose some, or coat it with gold, you might lose some of those details, but now that doesn't have to be the case. And what's also cool is because you can have different phases, you can actually study the interactions between solid and liquid phases like you were telling about.
Super, super cool. So we've barely touched the surface. There's so much more that we could talk about. We need to do a whole nother episode on backscatter diffraction. You can do diffraction with electrons. We should talk about TEMs. You can make micro machines that live inside of these SEMs, so you can deflect things and measure all sorts of mechanical or other properties on tiny microscopic objects. There's a whole world out there. But in this episode, we hope we've given you a flavor of electron microscopy, what it is, where it came from, and the basics of how it works. Now, before we go, a quick Q&A section. One of the questions I got recently, which I'd like to pose to my fellow co-host, is what, in your opinion, has been the most important or impressive scientific discovery of all time?
That's a pretty tall order.
Yeah, right. It's a pretty superlative. Just pick one that has impressed you.
I mean, one thing that I always thought was really amazing, I took an introductory physics course at a community college. It wasn't even calculus-based. It's not real. But I remember it was
real.
And so what I remember being incredibly fascinating, it's still fascinating to me today, was the discussion of light being both a wave and a particle. And once we discovered that, just our understanding
quantum mechanics
of the world and quantum mechanics completely exploded, and we were able to understand atomic systems in much more depth and understand even things like gravity and how that can bend light. And so I remember just hearing about that was just incredibly impressive to me, and it's something that I think about a lot, even to this day.
Okay. I'm going to cheat and give the response that I heard my PhD advisor give. I love the guy. He was Dr. Clark, David Clark at Harvard University. He's a great guy. And he would regularly talk about the marvels that technology, the great gifts or something that technology has given to mankind. And I'm forgetting the third one, but the first two was the p-n junction, and the other one was energy from fission. So the p-n junction, we should do an episode on this later, but essentially if you have a semiconductor and it's p-type next to n-type, that is the basis of transistors. It's the basis of diodes. It's the basis of photovoltaics. So many technologies. This has enabled enormous number of things. The p-n junction, something as simple as that. And the other one, energy from fission. I love renewables, but pragmatically speaking, I realized that you don't get sun when the sun's not shining. You don't get power from the wind when it's not blowing, and so you need to be able to store these things, and that is not a problem that we've easily solved. And yet, meanwhile, in the background, we've got nuclear energy from fission basically saying, like, what about me? And it's this incredible resource. So those are two things that stand out to me. I'm just going to steal his answer.
All right, as always, we are going to be dropping the list of resources that we use to learn about this in our show notes, so that if you're interested in taking your knowledge and exploration of SEMs and material science further, you can read through those and learn a little bit more yourself. As always, if you have any questions or feedback, please send us emails at materialism.podcast@gmail.com. Make sure you subscribe to the show on iTunes, Spotify, Google Play, or wherever you find your podcasts. If you like the show and you want to help us reach more people, consider leaving a review. It helps us improve, and it exposes us to new people and lets them find the show. Finally, check out our Instagram page at materialism.podcast. We post lots of cool infographics that correspond to each episode, and we like to post other things that help you dive a little bit deeper, so definitely check that out. And as always, we'd like to give a huge shout out to Alphabot for allowing us to use his music within the podcast. You can check him out on Spotify. And a thanks to Colabyte, who created the intro and outro for the podcast. He makes a ton of really cool synthwave music, so you should check that out as well at colabyte.bandcamp.com. Catch you next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world, and are bound only by their imaginations in manipulating those materials.